Alright, so we've covered our two individuals, Alice and Bob, here wanting to send a message to one another, our friends Alice, right? Hello, Alice. And our friend Bob. Right, and perhaps they're on the opposite side of the world, perhaps they're neighbors. Either way, Alice wants to send a message to Bob, but neither of them actually want their nosy neighbor. They don't want their friend Eve to be able to listen in on this message. Maybe it's a surprise birthday party, maybe they don't want Eve hearing their dinner plans. In either case, Alice and Bob here are saying, hey, we want to set up some sort of crypto system that can send encoded messages such that any outsider without what is known as the encryption key, right? And the outsider without the encryption key will not be able to listen in on this string of messages going between Alice and Bob. And so naturally the question here would be, how do you establish this encryption key? Quite clearly, prior to the establishment of the crypto system, right, we don't have a secure line to discuss things over. And because Alice and Bob don't have that secure line to discuss things over, when first contact is made, which is actually the first step, right? When contact is made, there is no secure line to establish encryption key, which poses quite a large issue because anyone with their hands on the encryption key will be able to decode these messages. And so naturally the question is, how do you establish that encryption key? And so in 1984, two individuals, Charles Bennett and Gauss Brassard, actually developed what was known as the BB84 encryption protocol. And we write out that name right here, BB84 encryption protocol. And if you can't entirely remember exactly why it's called this weird, Star Wars-esque style name, essentially the BB, right, comes from the last the last names of our two inventors, and the A4 comes from the year that it was invented. That's just a little bit of background for you. Now, when we talk about the BB84 protocol, what it essentially does is it's going to be taking two sets or a series of sets of orthonormal bases, right? And so in this case, just to briefly recall and remind you guys, when we do want to establish this encryption key, right, it's going to be a string of numbers. In this case, we'll say a string of numbers. And for our specific purposes, we'll say these are binary digits. So it's just zeros and ones. Right? And we're going to be using quantum computers essentially to establish this encryption key. Now, when we have that, right, like I said, we uses a set of standard of ordered orthonormal bases. And so the two primary ones that we'll be looking at today are 1, 0, 0, 1, right? And hopefully this seems a little bit familiar. This is our standard orthonormal bases, right? And our second one would just be, in a 90-degree direction, just for our purposes today. And 1 root 2, 1 root 2. Now, you may or may not recognize these, but in the case that you do, you might realize that this first ordered bases right over here, our standard bases, essentially takes spin and is attempting to measure it in the 0 and 180-degree direction. So 0 and 180-degree directions. It's like essentially taking on a circle, asking, hey, is your spin pointed upwards or is it pointed downwards in any case? Now, on the other hand, if you look at our second orthonormal bases that we very nicely have written out over here, what we are looking at here is measuring spin in the 90 and 270-degree directions, right? Very cool. Right, 90 and 270-degree directions, the arrows are a little bit lopsided, but that is perfectly okay as long as you get the concept behind it. Now, the thing here is that we're measuring in the 0 and 180-degree directions, going back to our first one, right? That is essentially attempting to measure things in the vertical direction, so vertical. And so we'll call and refer to this basis just here on out as the V bases. And because we're measuring for our second orthonormal bases, 1 over root 2, negative 1 over root 2, 1 over root 2, and 1 over root 2, right? In the 90 and 270-degree directions, we are essentially measuring things in the horizontal direction. We'll call this bases H for horizontal, just following this general naming convention. Alright, so now that we've essentially established our two primary orthonormal bases that we will be concerned with today, let's keep in mind that we've got to have some connection between it and the string of numbers, right? We got to have some connection between the orthonormal bases, which are clearly vectors in this case, and the string of numbers, which are ones and zeros. And so because these are ordered orthonormal bases, keep in mind that the order of our items will indeed matter. And so we'll just say for our purposes, our first vector in each of our bases, it corresponds to 0, and the second one corresponds to 1. So in the case that we measure spin in direction 1, 0, essentially we are receiving information of value 0. Now, in other words, just to kind of word it a little bit differently, let's say Alice wants to send, say our friend Alice, and we'll make her name pink, just for color coding purposes, and we'll make Bob blue, right? And then maybe Eve green, but we'll get to that in half a second. Now, when Alice wants to send a message, Alice is like, hey, I want to send a 0 measured in the horizontal direction in this case, right? And so Alice is like, all right, so if I'm measuring in the horizontal direction, I'll be using our second orthonormal bases right here. And she says, okay, so now that I have that, what would a vector corresponding to value 0 be? And in this case, it would be our first vector here, 1 over root 2 and negative 1 over root 2. And so she's going to be sending essentially a particle that's measured in this direction towards Bob, and Bob will measure, of course, and try to interpret it on his side. Alright, you might say this is all nice, very cool, but what does this relate to essentially trying to establish an encryption key? And, well, let's not get ahead of ourselves. First of all, we have Alice here, and Alice is going to say, hey, I want to send a message to Bob. So Alice is like, I want Bob, I'm going to send a message to you. And here's the thing, she's going to be choosing essentially a series of numbers, and so she's going to come up with some string. It could be like 0, 1, 0, 0, 1, maybe like 1, 0, or 0, 1. I cannot entirely word what's going on the screen, but in either case, she's going to be choosing her string. Now, she needs to be able to send that information over to Bob in the form of qubits, right? Because she's saying, all right, I'm going to be using quantum computer because it's cool, because I'm neat, and because, she's technologically advanced. I'm not entirely sure what the justification for that would be. But regardless, Alice is choosing the key, and so she's chosen this key, she's chosen this string of classical bits. And so, in order to send it to Bob, she's going to be choosing for each individual bit a corresponding basis to measure. And keep in mind our two choices for bases, right? Our bases choices are vertical versus horizontal. So she's going to be choosing either to measure the qubit for each individual bit here, each individual little bit, in either the vertical or horizontal direction. Now here's the thing, this is where things get a little bit interesting. What Alice is going to be doing is she's going to be choosing either the vertical or the horizontal one's bases randomly, but with equal probability. And so you might say, all right, what does that mean? Does that mean that there's a total of 2 to however many bits? Let's say there's 4n bits, right? And some integer, some real number, some positive number, right? And does that mean there's 2 to the 4n possibilities? Well, technically speaking, yes, but technically speaking, also no. The reason being, keep in mind, we're doing it with equal probability, keyword equal probability, or key phrase, I suppose, in this case, equal probability. And by equal, we're going to say, approximately half are going to be measured in the vertical direction, approximately half going to be measured in the horizontal direction. It's just a question of, what order are we going to be doing that in? Approximately. Now, you might say, all right, why do we use, in this case, then, a total of 4n digits in this string? We'll get to that in a moment, because actually we'll be cutting down on the string in a few seconds. Now, when Alice chooses each basis, she's going to say 0, or let's say we measure in vertical, maybe the horizontal, maybe vertical, maybe horizontal, vertical, and horizontal, and so on and so forth. And she's going to be assigning bases a direction of measurement to each. And so she does that. She does indeed send Bob the qubit consisting of the appropriate basis vector corresponding to each. So in this case, because she's measured it in the vertical direction, and it's also corresponding to 0, she's going to be sending Bob a qubit, and this is a qubit measured with a direction corresponding in this case to 1, 0, and because she's measuring the horizontal direction here, and so 1, and we know it's 1 over root 2, 1 over root 2, right? And then in this case it would be 1 over root 2, negative 1 over root 2, and so on and so forth. She's going to be sending a qubit measured in the corresponding direction. Now, and what's important to keep in mind is that Bob does not have the information regarding what direction Alice has measured these qubits in, meaning that it is unknown as to whether she measured in the vertical or horizontal direction, because Bob does not know that on his side. All he knows and all he receives is 1. All that Bob has, let me write this down, 1 is the choice of directions. Choice of 2 bases, right? He can essentially measure the qubits in. And 2, the second information that he receives is a set of qubits. Set of qubits created by Alice. All right, and these two are what Alice sends out and what Bob receives. And so Bob's like, okay, so now I have this string of qubits. And so what is she going to do? Now keep in mind the string is 4n binary digits long, and so she's going to be using a string of length 4n consisting of, this many 4n qubits, and also she's going to hold on to a string consisting of a total of 4n v's and h's, depending on what direction she's measured it in. Now Bob, on the other hand, receives this string. And let me very briefly just make sure I clear the space. All right, so Bob on the other hand, maybe across the world again, like I said, or maybe just even the neighbors. Now Bob receives this string of qubits, right? And he's like, okay, so I have all these qubits that I've received. But here's the question, what direction should he measure them in? Now Bob does know that he has 2 bases to choose. And so what he's going to do, he's going to choose 2 bases at random and with equal probability. And then he's going to say, all right, so I'm going to take this qubit and I'm going to randomly choose between V or H, measuring the horizontal versus the vertical direction, right? So again, Bob has a choice between the vertical or horizontal bases. And what's interesting here is that instead of trying to create the cubes, in this case, Bob is attempting to read them. That is important to keep in mind because this will actually relate to how we interpret Eve's actions in a moment. So going on from there, for each qubit that Bob receives, he's going to randomly choose bases. So let's say he does like V, H, V, 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 H, H, right? And keep in mind, in this case, again, he's going to be choosing them with equal probability. And so he's going to measure them. He's going to probably come up with a string that may be like 0, 1, 0, 0, depending on his measurements, and so on and so forth. Now keep in mind, in this case, Bob's actually going to be storing the information for both strings, and both are of length 4n. And the reason he's going to be storing the information for both strings will come up in a moment. Now that Bob has essentially 2 strings, and Alice also has 2 strings on her end, right? So what we can say here is just looking from probability, like a probability perspective. Let's consider all the possible choices there are. So let's say if Alice chooses vertical, or she chooses a horizontal, right? Bob has a chance of either choosing vertical or horizontal for each qubit. And now what we know just from looking at all the possible combinations and knowing that they occur with equal probability is that exactly half of the time, right, 2 out of 4 times, so that'll be half the time, 50% of the time, Bob will be choosing the same bases as Alice. So, what can we conclude from this as a result? Now, if there was absolutely no interference between this transmission of messages between what Alice and Bob kind of agreed on, right, and such that, there is no eavesdropper attempting to get in and read these messages, what we do know is that half of the time Bob's and Alice's bases will match, and as a result, half of the time, so with no interference, half of the time, the bases match. And because half of the time these bases match, what we can essentially say is that the information, right, between choosing the qubits or the bit values, either 0 or 1, will be the same. 0, 1 is the same, right, are the same. And the reason for this is essentially saying, analogous to trying to read the spin of a particle, right, and sending it through an apparatus measuring the vertical direction, and sending again through an apparatus measuring in the vertical direction. It's like saying, you're asking this particle, hey, are you oriented upwards? And if the answer is yes, and you ask the same exact question again, hey, are you oriented upwards? Naturally, the answer would be yes, both times, because the same question was asked consecutively to the same particle, or in this case, the same qubit. So now going on from there, now we know that half of the time for 2n of the string of qubits, right, because 4n over 2 is equal to 2n. Right, so for 2n of these qubits, their bases will indeed match. We know also that for the other half of the time, right, there is something quite curious, because keep in mind that when we essentially attempt to translate between our vertical and horizontal bases, we do know that for some values, some measured values, say 0 in the horizontal bases, half of the time Bob here will measure as 0, and half of the time Bob here will measure as 1. So half the time for these 2n right here, he will be wrong. In general, this is just a question of translating between bases and saying, hey, you know, what are the probability amplitudes corresponding to each, and what are the probabilities of getting spin measured in some direction. Now, half of the time in this case is a little bit too much left to chance. So actually, we're going to be focusing on the cases actually where the bases measured between Alice and Bob are indeed the same. So what they're going to do is Alice and Bob are going to correspond over an unsecure network, one that's unencrypted. And they're going to ask each other, hey, when do your bases match? And they're going to compare their string of bases, not their string of values, not their string of encryption key values, but their string of bases, and they're going to figure out which ones match. And so as a result, we are left again with a string of length 2n. Right, so a string of length 2n. Right, and so both Alice and Bob have this string. And so they're going to be keeping only the bits where their bases match. So bases match for these bits. Alright, so I'm going to make a quick diversion, a quick digression, just to talk about what Eve can do in this case. And we'll have Eve represented, let's say, with green, right? And so Eve here, Eve's like, hello, I'm going to attempt to listen into your messages. And what Eve is doing here is she's going to have to be able to obtain information from these qubits. And so she's going to attempt to intercept these messages. Now, when Eve is stepping in to intercept these messages, right, when you have this message string, right, and you're sending qubits across the space, and Eve's like, hey, I want to listen in. Let me in on this little line here. There's a couple things that she can do. Ideally, if we're talking about classical computers, what she would do is essentially maybe like make a copy and then give one to herself, right, and then send the other copy on to Bob. But here's the issue: whenever she makes a copy, and let me make sure it's clear, we're talking about making a copy here. Whenever she makes a copy, the thing is with qubits, you can't actually read a qubit without trying to interfere with it. Because the thing here is that whenever you read a qubit, you are naturally trying to read it in some direction, because you can't obtain information just by looking at a qubit quite naturally, because that's not how qubits work. And so whenever she makes a copy, essentially she's going to be interfering with the information that she receives. And so when she intercepts the qubit between Alice and Bob, right, this essentially she has to measure the qubit. And in order to measure the qubit, she has to measure it in some direction, right? She has to measure it in one of the two basis vectors, either vertical or horizontal, right? In order to determine the direction this qubit is attempting to tell you, or the information stored within this qubit. And from there, she measures the qubit and then sends it on to Bob. Now, in the case that there is some interference between Alice and Bob, let's talk a little bit about what happens. So keep in mind here, Alice and Bob, again, are only interested in the cases where they chose the same bases, right? Our 2n string, our lovely 2n string right over here. Hello. Now, this, like we said earlier, in the case that they did choose the same bases and there was no interference, we know that these strings are the same. But in this case, Eve is interfering, and because she has read something in between, she has attempted to interfere. Now, what we know, let's say, for instance, that Eve is choosing a series of bases. Now, what Eve is going to do is she's going to say, hey, I have a total, I have all these bits here, right? She has all these bits. And for each of these bits, what she's going to do is she's going to be randomly choosing, in this case, perhaps with equal probability, perhaps not. But let's say with equal probability, she's going to be randomly choosing between the horizontal and vertical, right, bases. And so now we know that for every combination, right, we have Bob, we have Alice. Let's start with Alice in this case. So we have Alice vertical and horizontal. We have Bob measuring in the vertical or horizontal directions. Vertical or horizontal directions. And then we have Eve on the other hand. And now we know that half of the time Eve will be measuring in the same direction. This is not a probability tree, by the way. I apologize. It's not, perfectly drawn. There's definitely more possibilities. If I was to draw all of them, it would look something like this. Something like this. Right, and these are all our probabilities and our possible combinations that we have. Oop. Oop. Apologize for my very sad looking lines. Now, just based off of this, we know that half of the time, in the case that Eve is choosing the bases that she measures these qubits in with equal probability, we know that half of the time, Eve will be choosing the same exact bases as both Bob and Alice. And the reason this is the case is because we've already taken out all the cases where our bases do not match, right? And so what that actually leaves us with is a case, and let me make sure this is a little bit neater just for interpretation purposes, is that in fact it would look like this. Just looking at the bits that we've already singled out, we know that Alice and Bob have bases that match. So vertical, and horizontal, right? And so now Alice is choosing them with equal probability. So vertical, horizontal, just out of the bits that we have left. And so we know that half of the time, all three of their measurement directions will indeed match. Whoop, right? Half the time. So 2 out of the 4 possible chances in this case, given that we've already restricted perhaps what exactly we are looking at. And so now, looking at this series of 2n bits, right, we know that approximately like a quarter of Bob's bits will end up actually disagreeing with Alice's. And the reason for this is that when Alice attempts to measure in the opposite direction, we know that about half of the time, right, she will be right, and half of the time she'll be wrong again. The same goes when she measures again in the opposite direction. Half the time she'll be right, and half the time she'll be wrong. And then when Bob measures it again, we know that he is essentially trying to measure it again in this other direction. So we know another half of the time will be right, and another half of the time will be wrong. Right, just because it's going from Alice, who's measured in the vertical direction, looking at this first case right here. Alice measures in the vertical direction, Eve measures in the horizontal direction, so only half of the total qubits here will be right. And then Bob again measures in the vertical direction, so half of the half, which is equal to 1/4, of the qubits here will be right. And again, 1/4 of the qubits here will be right. So 1/4 of the total qubits here will be accurate in this case, and 1/4 of them will match in these scenarios. And let me be clear, I apologize, I realized that might have been a little bit confusing before, but actually what we're looking at is just 1/4 for each individual case here. And so as a total amount, actually half of the qubits in this case will actually disagree with one another. And it might be a little bit easier if I kind of break it down from just like a tree perspective. So first of all, we're looking at bits, a total of 4n bits, right? We start with 4n bits. And then they compare the strings, and then we break it down to 2n bits where bases match, right? And now we know that in the case there is interference, so with interference, we will have unmatched bits in this 2n long string. So we'll have non-matching bits. I'm not entirely sure if non-matching is a phrase or even a real word here, but in this case, there are bits that don't entirely match here. And in the case there is no interference, we'll have all bits match. All bits are okay. Alright, so now what goes on from here is actually we now have a string of 2n. We need to be able to break that down and make sure that Eve in this case has not read any of the bits. And in order to do so, actually, let's save a little bit of our time, right? And let's say, alright, so now we have 2n strings. And what Alice and Bob are going to do is essentially they're going to say, alright, Alice and Bob, they're each going to take half of their strings, and they're going to be corresponding qubits, and they'll be selecting exactly 1n, and they're of the bits, right? And there's say 1n, 1n, apologize, they're both blue in this case, and they're going to be comparing this string of 1n digits, right? And if this entire string matches, and if all of it is the same, then we can say quite safely that Alice and Bob have not had anyone attempt to intercept and read their communications, and so they can use the remaining 1n of the string that has not been revealed over in the secure line, right? They've compared these two, and that leaves 1n. Right, and they can essentially use the remaining 1n n length string of numbers as their encryption key. Now, in the case that this 1n length string that they've isolated from the other half of this string does not match for some certain probability, let's say roughly a quarter of the total length, then we know in this case that Alice and Bob have indeed had an eavesdropper in their conversation. As a result, they will need to find some other way to establish the encryption key. So this is just a nice way to check and make sure that no one has attempted to interfere with this line of communication when establishing the encryption protocol and sending these qubits between one person and another. Right, so just to briefly recap, essentially what we had a little bit before, right? We had a length of 4n bits, and Alice chooses and comes up with the value for this encryption key. So 4n encryption, or here, 4n string of bits, not quite yet encryption key, string of bits, right? And then both of them randomly choose between the bases vectors, randomly select bases. And then from there, they measure the qubits, right? And Alice measures the qubits, sends it to Bob, and Bob measures the qubits. And so we know that for 2n strings, a 2n long string of bits with bases that match between Alice and Bob. Right? And from there, what they do is select 1n a long string and compare the values. Right, so within this string of 2n where the bases match, right, they compare the values of half of these bits that they have. And so in the case that these values all match, you have no interference, and thus use the remaining remaining 1n string that has not been exposed and has not been compared, because just from process of elimination, we know, actually not from process of elimination, but we just know that there has been no interference. No one has listened in on this string. Now, in the case that any of the values have discrepancies, when compared, discrepancies, oops, and we're getting to the bottom of the page here, so I apologize for the handwriting. Discrepancies. I am no spelling bee champion here, right? When we have discrepancies in this case, and I apologize, and that means that there has been interference. It is an attempt at a check mark, right? And so as a result, we'll have to reestablish another string of bits. We'll have to find another way essentially to establish this encryption key. And so that is essentially the BB84 protocol in a nutshell, right? In a nutshell, it allows you to double check and make sure that no one has attempted to interfere with this establishment of an encryption key during first contact. And so as a result of that, we are able essentially to kind of make sure that Alice and Bob here can set up this secure crypto system without Eve listening in, without Eve and our eavesdropper and our general public, obtaining a value of your given key, in this case, the key that allows you to decode all the messages. Alright, so that is it for today. If you have any questions, as always, please do not hesitate to reach out or check out the Community Quantum Tech website. And as always, stay curious and keep on learning. Thank you.